What's up, you guys? Welcome to Integration B Training for Beginners Part 4. We will be working on trigonometric integrals. So it's going to be a lot of practice on trig identities and some manipulations. Let's go ahead and start off with the first integral. Sine square cosine cube. Okay, so we see that we have sine square cosine cube. So we're going to have, so I would want to leave out cosine x, right? And the reason behind this is because we can do a u substitution where u is equal to sine of x and du is equal to cosine of x. And with this cosine square, this equals to sine square, right? Sine square, 1 minus sine square, right? And then cosine x. Okay, and then it's u substitution here. Now, going a little further back, in integration B, if you remembered from integration by parts, I like to abbreviate sine and cosine. So it's a little easier, it's a little faster to sort of go like this. Okay, we got sine square, 1 minus sine square, and then cosine here. Let u equal sine of x, then du will take over that, and then we end up with u square, 1 minus u square, which is equal to u squared minus u to the power of 4. So this will give us u cubed over 3, 5 over 5. So the whole integral would be sine cubed 3 minus sine to the power of 5c. And then we have our answer. I like to abbreviate mines. It's just a little faster. Next integral, from 0 to pi over 2, we have sine to the power of 5. So here, I'm going to introduce you a new trick very early, just to help save some time here. So with this integral, there is this trick. It's called Wallis trick. Okay. And this works for all, it has to be from 0 to pi over 2, okay? From 0 to pi over 2, and it works for sine of x and cosine of x, okay? It works just for both of them, all right? And the way it works is if n is odd, then we start with, so the answer, we start with 1, and then 2. I'm sorry, no. We start with 2. That's right, because the odd number is at the bottom. The odd number has to be at the bottom. So if n is odd, it's 2, 3, 4, 5. And this will be your answer for this one, right? And then if for any odd number, n odd, you keep going until you reach to your odd number n, and this would be your answer. Okay. If n is even, then you start with pi over 2. You start with pi over 2, and then you do 1, 2, 3, 4, and you keep going until you reach to your even number, n. And this would be your answer. So this is called Wallis product. And Wallis trick is very, very helpful, super helpful, and it comes a lot as well in integration B. So in this case, this answer, instead of computing some tediousness, right, we could just go ahead and go straight into Wallis' trick. Oh, okay, this is 2, 3, 4, 5. This is equal to 8 over 15. And that's your answer. You're done. You're good to go. That's all it is. So I see there's an x squared here and there's an x here. So it looks like we can do some u substitution, right? Let u equal x squared. And so what this will give us is half cosine 5u. Oh boy. So we have cosine 5. Well, what we can do is we can let cosine, just one cosine out, and then we end up with cosine to the power of 4, and we can turn that into 1 minus sine square squared, right? So we want to utilize cosine and turn it into a bunch of, in terms of sine, so that we can perform u substitution. So the cosine to the power of 4, we turned it in terms of 1 minus sine squared, and that's that squared. So that u equals sine of x. And now our du would take care of this, and we end up with a half of 1 minus u squared squared. A little bit tedious, but let's go ahead and do it quickly. Okay, and so then we have half sine 5x, 5, minus 2/3 sine cubed plus sine of x. And this would be our answer. Well, so this one's a little tricky, right? You would think you can do u equals sine x, but then you don't have cosine here, right? There's no cosine to leave out. So in this case, we have to use a trig identity, and that is sine square is equal to 1/2 minus a half cosine of 2x. So this is a good trig identity you must memorize, because this occurs a lot in integration B. Now, a good safety tip: if you don't remember that trig identity, here's what you can think about. Think about cosine of 2x. Okay, this one, remember this one. Okay, I hope it's easy for you to memorize, and it's cosine square minus sine square. Okay, cosine of 2x is equal to cosine square minus sine square. So memorize this, because this looks a little easier to memorize, right? Because it kind of looks like a pattern. And then think about, okay, well, cosine square can turn into 1 minus sine square. Okay, and then this would become 1 minus 2 sine square. And then what you do is you solve for sine square. Okay, then let's see, sine square is equal to, 2 sine square is equal to 1 minus cosine of 2x. And that's where that half came in. Sine square is equal to 1 minus cosine of 2x over 2. So that can be your emergency backup, for your memory, right? So just remember this, and then sort of derive on to here. Okay, I know what to substitute for sine square, right? But in general, if you keep practicing a lot, you'll start to develop the memory. Oh, okay, sine square is equal to half of minus half of cosine 2x. Okay, and that's what we're going to substitute. So it's this, and that's the easier integral. So this is just x over 2 minus, and then so that's sine. Don't forget that 2x divides, so it's 1/4 sine 2x because of chain rule, and then that's your answer. A little bit more difficult. So here you have cosine to the power of 4. So we're going to let cosine square. We're going to substitute cosine square with 1/2 plus 1/2 cosine 2x. This is another trig identity that's helpful to memorize. But again, it follows the same backup memory method where, okay, cosine square minus sine square, turn this into 1 minus sine square. And then you'll end up 2 cosine square minus 1. Oh, okay. And then solve for cosine square, and you'll end up getting like 1 plus cosine 2x over 2 equal cosine square. Okay, so that's where all that comes from. Now, we apply that to the integral. Right, so it's 1/2 plus 1/2 cosine of 2x. Now, this is cosine 4, so this means that we have to square it, right? So we're going to have to square it. So this will give us 1/4. And then this times 2. That's still 1/2 of cosine 2x. And then plus 1/4 cosine squared 2x. Okay, a little tedious, so let's go ahead and integrate all this. All right, so this becomes x4 plus 1/4 of sine 2x. So I just want to integrate all of that, and then we're left here with 1/4 integral cosine square. We use the same trig identity, except that this is 2x, so now we're going to turn it into terms of 4x. So now it's 4x now, because we double it. Okay. So now, oops, I have to go like this. I just need more room. Okay. So now this is equals to x4 sine 2x plus 1/4 x over 2, and then 1/4. Oh, ooh, careful, careful. That's not 1/4. We're dividing by 4, so now that's 1/8. So sine of 4x, not 2x, plus c. And that's our answer. This looks like sine x, cosine x. That reminds me of sine 2x, right? So we can use sine x, cosine x. We can substitute it with sine 2x over 2. And because it's being squared, this would be sine 2x squared over 4. Okay. And then 1/4, we use the same trig identity. Just be careful, it's 2x. So now this would be in terms of 4x, because we double it. Okay. And so now we go ahead. This is just, well, we can technically factor this out, right? So this would be 1/8, and this is x minus sine of 4x divided by 4 because of chain rule, and then we're done. Okay, so what do we do here, right? So I want to drag out cosine x. The reason why I want to do that is because we can turn cosine 4x in terms of sine of x's. That's why. And then if we can do that, we can do a u substitution. So sine cubed And then cosine to the power 4 will become 1 minus sine squared. And then we have cosine here. And that will help us do a u sub. U equals sine of x. The du will take care of this. We get u cubed 1 minus u squared. It's a little tedious, but let's just, sometimes we just have to sort of absorb some balls to do the algebra. And then this simplifies to u cubed minus 2u to the power 5 plus u to the power 7. Okay. Simplified. And now we go ahead and integrate. This would be our answer. Or minus, this would be 2 over 6, that's 1/3. Plus 8. That is our answer. Alright, so then we simplify this. We get 4 minus 4 sine of x plus sine square. Okay, cool. So then this would become, so this is 4. So whenever we have a constant, most of the time, if it's just a constant, it's just going to be c times b minus a. Because I mean, this is just cx, and all you're doing is it's just b minus a. So that's a good thing to sort of keep in mind, and it just helps us to do this mentally. So technically this is 4 times pi over 2 minus 0. So this is 4 times pi over 2, this is 2 pi. Okay, minus 4. Ooh, hold on. What do you notice here? 0 to pi over 2? Huh, we can use what? We can use Wallis' trick. Okay. Well, because this is just sine of x. Here, sine of x, you can't do Wallis' trick because this is just 1. So, but that's okay. I mean, it's an easy integral. It's a very easy integral. So you can just simply integrate away. Pi over 2, 0. This becomes, okay. So this becomes 0 minus 1, right? I think I did that correctly. Cosine of pi over 2 is 0. Yeah, and then the reason why it's positive is because the negative cancels out. So, okay, so that's negative 4 there, and then plus, and then sine square. Now we can do Wallis' product. So because it's 2, it's a half pi over 2 times 1 to 2. We stop here because it's 2. Okay, so this is equal to pi over 4. Pi over 4. Huh. I hope I did this correctly. But then, so our answer would just be 2 pi plus pi over 4 minus 4. Alrighty. So this is a secant cube, then tangent x. So of course I would put this in terms, because we have tangent x and there's only one tangent, but we have multiple secants, then we will do u equal secant x. And then our du will take care of that tangent x here. Okay, so now this is secant cube, so that means that we will be formatting this as secant square here. So our d, so in the u integral, there will be u squared du. So this is just simply secant cube over 3 plus c. Ooh, all right. So now, this is sort of in terms of even numbers. We can take out secant square. Why do I want to do this? Because we can turn this in terms of tangent. Okay, we can turn this in terms of tangent using the trig identity tangent square plus 1. And then when we let u equal tangent x, our du can go ahead and take care of secant square. So now this becomes u to the power of 4. Again, this requires a bunch of tangent squares. I'm sorry, secant squares. So this is secant square squared. So we're going to have to square this, and then it will be u squared plus 1, and then du. Cool. Now, a great trick is we can absorb the exponent, right? So if I go like this, u square squared, we can absorb it because the exponent here, they're the same. So this would be u square plus 1. And this gives us u4 plus u square squared. And then we can turn this, let's see, if we square it, give us u to the power of 8, 2u6 plus u4. Okay, so this whole integral is going to be tangent 9x over 9 plus 27 tangent 7 1/5 tangent 5 plus c, and you're good to go. Ooh, so what do we do? What are we going to do? So because we don't have enough secant x to do a u sub with tangent, but we can do u equals secant x. And the reason is because we can separate this with tangent x, secant x, and this tangent x, we can put this in terms of secant x, right? Because tangent square is equal to secant square of x minus 1. And so this could be secant square minus 1. And then our du here, right? So letting u equal secant x, we get u squared minus 1. Oh, okay, easy peasy. This is just secant cube over 3 minus secant x. And then we're done. What the heck? This looks a little awkward. Tangent and cosine, we don't have a derivative that goes together with that. So in this case, what I like to do is I put everything in terms of sine of x and cosine of x. Okay, well, I know tangent square is sine square over cosine square. And we have cosine cube. Oh! It cancels out, and then we have 1 cosine left. And so we have s square, sine square and cosine. Oh, okay. Then let u equal sine of x, because we can have du take care of cosine of x, which is what we have here. And so this becomes u square du. The answer is just sine cube 3. And that's it. Ooh, I like this one. This one's a sneaky one. So, I mean, you could do it regularly on both sides, or watch this. What I'm going to do is, because these are tangent squares, let's see, if I factor out tangent square, what's going to happen? I get 1 plus tangent square. Oh shoot, and that equals tangent square secant square. Oh shoot, and our the derivative of tangent x is secant square of x. So we could do a u sub tangent x. Du will take care of this. So then we end up with u square du. This becomes tangent cube over 3. just like that. What are we doing here? So, I guess I can show both ways, the beginner way and the intermediate way. The beginner way is longer, but it's just easier to process. That's all. So the beginner way is turning this tangent 4 in terms of tangent square. Then our tangents, the other tangent square becomes secant square minus 1, right? So now what we have here is tangent square secant square minus tangent square, right? This here, this is just a u substitution. So let u equal tangent x, and then your du is secant square. Then you end up getting tangent cube of x over 3 minus, and then here, this is one of the integrals that you should already have memorized by heart. So this is tan x minus x plus c, and then that's your answer. So that's the beginner way. The intermediate way is whenever you have tangent x to the power of something, then we kind of do a geometric polynomial division. So what that means is you let u equal tangent x. If you're a beginner, skip this. This is just for intermediate users. Your du is secant square. But we can do a forced u substitution because this is 1 plus tangent square. So this is 1 plus u square. So meaning that du, 1 plus u square, is equal to dx. Okay. I'm just being lazy. But so here, this becomes, okay, well, plugging in 0, pi over 4, 0 to 1. Okay, and then we have u4, 1 plus u square, du. Right. And so now we have a geometric polynomial division. And the way it works is, okay, you have u to the power of 4, you're doing plus u square minus u square, then plus 1 minus 1, etc. So what this does is it divides, and so factoring this, you get u square, and everything cancels out, right? So how it goes is it geometrically goes off in a pattern. It's kind of like this, right? It's like this, and then, oh, okay, so this is x minus 1, x and minus 2, and so on until it gets to here. Okay, this is what I mean by geometric polynomial division, right? It's the same concept, but with x, but with u square. Same goes with here. Like if it was x cubed plus 1, right? Then this time it alternates. I believe the same goes for any odd number as well, right? And then it just alternates. Right? It alternates. So that's the geometric polynomial division. Oh no, I can't undo. So now the only difference, the difficult part about this is that you have to imagine it in terms of u squares now. So doing that, this becomes u square minus 1 plus this. Okay, and if I do it properly, you can double check. Okay, well, we'll do plus u square, and this portion just gives me u square, right? Minus u square minus 1, and then plus 1. Okay. Yep, my signs are correct. Cool. and then you're good to go. So you should end up with this from geometric polynomial division. And then this is easy. This is just, it's just u cubed 3 minus u plus inverse tangent, right? That 0 just makes everything 0. Plug in 1, and then we get 1/3 minus 1 plus pi over 4. And then that's our answer. Again, the fast way is using geometric polynomial division. So I'm going to do that first in this problem, right? Let u equal tangent x, right? And you're going to end up with using du 1 plus u squared equal dx, right? Because we let x equal inverse tangent of u. And so now this gives us u to the power of 5, 1 plus u squared, right? Again, it's very difficult to imagine, so that's why I prefer this for intermediate users. So divide u5 by square, that's going to give us u cubed minus u, and plus, I think it's u1 plus u squared du. Right, and you can double check, right? You can double check, okay, we want to cancel out the 1 plus u squared. U cubed minus u cubed minus u plus u. Yep, it's what we exactly have, okay? And then you go ahead and integrate. This is tangent 4 minus tangent square 2. And then this is plus a half of ln of, this is technically secant square, or ln of secant x, right? And then this would be the intermediate method. And it'll be, it's hard to visualize, but it is quicker. I find it a bit quicker. For beginners, it's going to be a longer process, because you have to consistently keep doing secant square every time. So taking the beginner's route, we have tangent cube, right? And then we have tangent x, tangent square, sorry. And we need to turn this in secant square minus 1. So we have tangent cube secant square minus tangent cube. We kind of have to do this again, right? So tangent x with tangent square, we turn that to secant square minus 1. Okay, so we have tangent cube of x secant square minus tangent x secant square minus, oh, careful, minus, that makes it plus tangent x. Oh, so a small trick here, you don't have to do u sub and then u sub, okay? You can factor out secant square. So this gives us tangent cube minus tangent x, and then tan x dx. Okay? And then you can go ahead and u sub this whole thing, this whole term here. And then you'll end up getting tangent 4x over 4 minus tangent square over 2, and then plus ln of secant x, which is exactly what we got before. Okay? All right, let's get into another trig identity. This one is a little difficult, but it comes up a lot in integration B. That is dealing with integrals like this. Okay, in a regular class, they force you to do integration by parts, right? In a regular calculus class, they would make you do integration by parts, and you would have to solve this integral in integration by parts. I do not like that. What I like to do is instead we're going to use a trig identity. Now, this is hard to memorize. I mean, I don't even know. I don't even have it memorized by heart. So here's what I do. There is a set of trig identities that you should have memorized, and that is just the angle sum. If you have, let's see, so here's how the concept works. So the sine of a plus b is sine of a cosine of b. Right. Actually, let me put this as plus or minus. Plus or minus, and plus or minus here, and then cosine of a, cosine of b. Okay. Oh, I'm sorry. Sine of b. There you go. So that's the pattern. It's sine, cosine, cosine, sine. So for sine, the angle sum for sine, it's sine, cosine, cosine, sine. Okay. And then, of course, it's just to make the angles alternate. That's all it is. So, again, sine of a plus b is sine, cosine, cosine, sine. And then it's just the same thing for here. It's plus or minus, plus or minus. So what this means is if I had something like sine of x plus y, then it would be sine, cosine, cosine, sine. And this is just to alternate for the angle. It's just to alternate x and y, right? And if this was minus, then this would be minus. Okay, so again, for sine, it's sine, cosine, cosine, sine, right? If we're dealing with sine, we start with sine. Okay, sine, cosine, cosine, sine. For the next trig identity, cosine. Then I'm going to do the same thing, plus or minus a plus or minus b. Now that we have cosine, we're going to start with cosine. Okay, just a good memory trick. And then the way the way it works is it's cosine, cosine, sine, sine. So it's like a double, it's like a twin now, right? For sine, it was like sine, cosine, cosine, sine. So it was like alternating, right? For cosine, it's like a twin here. And the way it works for cosine law, I mean, for this cosine trig identity, it's cosine A, cosine B, and here's where it gets tricky. Here's where it gets tricky. For cosine, the sign flips. The sign flips. So it's minus plus. And then sine, sine. Okay. So for cosine, it's cosine, cosine, sine, sine. Cosine, cosine, sine, sine. So if I have something like cosine x plus y, right, then this would equal cosine x, cosine y. Because it's plus, it would be minus sine, sine. Okay, so that's the trig identity. So this is the concept we will be using because I don't have my trig identity memorized for something like this, right? So here's how I do it. Okay, so we're working with sine and cosine. What trig identity does the sine cosine pattern? Sine, the sum of sine, right? it's this pattern here, right? Because the trig identity for this was sine, cosine, cosine, sine. Okay. All right. So we're working with sines. Okay. So sine, cosine, cosine, sine. I'll put plus here. Sine, cosine, cosine, sine. Put a minus here. Now, why on earth did I lay it out like this? Well, the way it works is we only have sine and cosine. We only have one sine and cosine. So here, what we do is we add 2 together, and it cancels these out. And so we get 2 of sine cosine, right? But however, this is equal to sine of some sort and then sine of some other sort. Okay, so that's how the concept goes, right? Otherwise, you would not want to memorize this trig identity unless you want to, if you're that committed. But it's hard for me to memorize this trig identity because I get mixed up with because the trig identity looks like this. Sorry, it looks like this. If you have say a, b, then it looks like this. A plus b. I don't know if it's minus, or I don't know if it was plus. It's something plus or minus. I don't remember. And then it was a minus b, right? And what tricks me is the minus part, right? Because sometimes you'll think it's it's this, but no, it could be the other way around. Maybe it's minus here and plus here, right? And that's what confuses me. And that's like, and I don't want to risk memorizing that because that's a pain. So what I do is, okay, well, let sine of 9x, right? That means that I added these two. So that's sine plus, okay, minusing will give me sine of x. So that's me minusing that. Okay. So now you're thinking, wait, Silver, this is 4x, this is 5x. Would it be negative x? Yes, it would be. But, I mean, because sine's an odd function, I mean, you could just go like that, maybe. But, anyways, continuing. So, yeah, this would be c. Let's see. So here, x here. So, actually, now I think about it, it does make a big difference because I would have to have a negative x here, and that would affect everything here. Yeah, you're right. You are indeed right. So, negative x, right? We have negative x. So I'll put that here. Okay. So then what this means is we're talking about sine 4x cosine 5x. That's what that means, right? Because I have negative x here. This is negative x. Okay, cool. Then we want this alone. So that means that we want this alone. Okay. So in order to do that, we must add. If we're adding, then we have to add this as well. Okay. So then this all subtracts. I mean, this all cancels out. This becomes 2 of what we have. 2 of what we have. So because of that, we have to divide it to the other side. So now this whole integral is equal to divide by 2 sine of 9x plus sine of negative x. Sine of negative x is equal to minus sine of x. Okay, and now you have your integral. So now this is equal to minus 1 over 18. Because of the chain rule, we divide by 9. And then plus cosine of x over 2 plus c. And that is your integral. Now, it may seem like that took very long, but that was only because I had to explain the concept of this to you guys, right? Now that I showed you how it works, it's a lot faster than integration by parts. It's a lot faster than integration by parts. And you have to get the hang of it. Again, you have to do a lot of these integrals to get a good sense of which is cosine, which is sine. Okay, so let's do another one. Cosine 2x, cosine 3 of x. It's the twin, the cosine. It's the twin. So that means we're working with cosines. Okay, cosine 5 of x. That's cosine minus sine, right? If we're adding, then the sign flips. Okay, cosine, all right. So, and then we subtract them. This is negative x. And so we have cosine plus sine here. Now, because we want cosine alone, we want to add. So this cancels out and we get 2 of this. Okay, we're going to have to divide by 2. All right, cosine of 5x. We could turn this into x because cosine is an even function. Dx. Okay, cool. And we're good to go. So now this is just 1 over 10 sine of 5x plus sine of x over 2 plus c, and we're done. That's it, right? A very, very fast, way faster than integration by parts. But this system here, you just have to get used to it, okay? You just have to get used to it. Just get used to it. All right, it's a sine, it's a twin. We're dealing with cosine. All right. So cosine, when we add 14x, so that is cosine minus sine. Subtract here, 6 minus 8, that's negative 2x. So because we subtracted, that's adding here. Again, it's opposite for cosine. Okay. However, we want sine alone. Oh, okay. We want sine alone. So we can't just add, because that will cancel out sine. We want to cancel out cosine. Well, here, in this case, that means that we would have to make this negative. Make this negative. Now this is negative, and this is positive. Now we can add. We get 2 times of this, and then we just have to divide by 2. All right, got it. Half. Right, now this is cosine negative 2x. Again, cosine's an even function, so we can just leave it as cosine 2x. But now it's minus cosine of 14x. You see why I don't like to memorize the trig identity of this is because it's too risky. So this is like a safer way to actually. It really helps me let me know like. This is how it is. So we have this, and now we just go ahead and straight up integrate it. Sine 2x, this is 4 because we have to divide by 2. And then we have to divide by 14 by chain rule. So this becomes 14 times 2. That's like 28. Yeah. And that is our answer. Takes a lot of practice. It takes a lot to get used to. So definitely practice on that with that method. We have 1 plus cosine 2x. So what do we do here? Well, for my trig identity, if you remember cosine 2x, from what I showed you, it's very good to memorize that. This is cosine square is sine square, right? This is also equal to 2 cosine square minus 1, or 1 minus 2 sine square, right? Now, I want 1 plus cosine 2x. So I need a 1 at the other side. And that means that we will be using this here, because I could just add a 1 to the other side. So now this is 1 plus cosine 2x is equal to 2 cosine square. That works. That will help cancel out the square root. Okay. So now what? So what does this equal? This becomes, oh, well, this is just a 2, so it's square root of 2. And then this becomes square root of cosine square x. Cool, so what does this equal? What does it equal? It equals to what? What does it equal? What does it equal? Cosine of x? Be careful. Be very careful. Okay? Because we have definite bounds, right? If it was indefinite, then yeah, then we're safe to just go like that. But because we're dealing with a definite integral, absolute value, okay? Don't forget that, you doofus. Absolute value. When we were square rooting, absolute value. Okay? Do not forget that. Okay? The integration B is not always nice. So they want to purposely eliminate you. So you cannot fall for that. But are we really safe though? Technically, well, let's see. Cosine, let's see, from 0 to pi over 6. Technically, yeah, we are safe. We are technically safe. We're still cosine of in this bound, in this domain. We are definitely in the positive still. So technically, this is indeed the same thing as pi over 6 regular cosine of x. Okay. I just want you to get into the habit of absolute value. That's all. I just want you to get in the habit of putting absolute values. Otherwise, you'll accidentally become too comfortable to the point where, okay, maybe if this was like from 0 to pi, right? And then you accidentally did this. You became too comfortable and you screwed up. You screwed up, right? You screwed up and then you're done for, right? Absolute value. Absolute value. Okay, and then in that case, that splits that to, I'm sorry. Yeah, it does split it. Positive here, pi over 2, pi, negative here, right? So again, it's just to get you into a habit of putting absolute values so that you don't accidentally become too comfortable with just not putting absolute values. So be careful of traps like that, okay? Be very careful with traps like that. So square root of 2, this is sine of x, because it's a simple integral. 0 to pi over 6, 0, we know that's 0. Sine of pi over 6, sine of pi over 6, here, this is 1/2. So, and then cosine will look like this. This is root 3 over 2, right? But we have sine of x, so sine pi over 6, that's 1/2. So our answer is root 2 over 2. Remember your trig identity. Remember your trig identity. Okay, this is not secant square. This is not secant square. Okay, it's 1 plus tangent square. Okay, they're doing this on purpose to trick you. Okay, when you go too fast, you'll think, oh, secant square, this cancels out. No, it's not x plus c. Okay, be very careful. Be very careful. All right, so this looks bizarre. So when something looks bizarre, you turn it in terms of sines and cosines. Okay. Secant square, well, this is at the bottom, so this simplifies to cosine square. And then we have 1 minus sine square, cosine square, because that's what tangent square equals. And then we simplify it, right? We distribute, and this gives us cosine square minus sine square. Ooh! Cosine square minus sine square. Remember what that equals? You should remember this is cosine 2x. So this is cosine 2x. And so the answer is a half of sine 2x plus c. So now, this is what I call trig conjugation. Trig conjugation. So, I actually, you know what? I want to change this. Actually, no, I'll leave it. I'll leave it. I'll leave it. So, trig conjugation. Trig conjugation. What do we do here? So, in trig conjugation, this means that I'm going to conjugate this with 1 plus cosine of x. 1 plus cosine of x. Why? Why, you ask? Because this is equal to 1 minus cosine square. And that equals sine square. So that helps simplify a lot better. So now what we have here is 1 plus cosine of x sine square dx, right? And now this just equals, if you just sort of put it in terms of sines and cosines, you'll notice that this equals cosecant square plus cotangent x cosecant x, right? And these are common integrals, standard integrals that we know. So this is negative cotangent x minus cosecant x plus c. All right, so what do we do now? Wait. Before we get into trig identities first, do you notice something sus? What do you notice? Right? Ah, the bounds. The bounds. You thought you would go straight into trig identity, do all that work, and then waste your time doing multiple trig identities, thinking you can simplify this. Well, guess what? An opponent will beat you in 2 seconds because this is secretly an odd function. Sine 2x is odd. Cosines, these are even. Okay? You thought you wouldn't get away with this. You thought you could just do trig identity and then do all the work. And then at the very end, you notice that everything equals to 0, and then you become sad that it's 0. Why? Because you've realized that this is an odd function. The bounds are opposite of each other. So this is all 0 by symmetry. Okay? Do not forget symmetry. Okay? Integration bees will hiddenly put that out. It would sneak in symmetry, and you wouldn't even realize it because you weren't looking carefully. So, don't you dare, how dare you try to do this with trig identity. Oh, cosine, cosine. All right, let's try this, and then we do another with trig identity. No! No! It's symmetry. This is an odd function. It's all equals to 0. Okay, I will not torture, I will annoy you to death to make sure that you remember symmetry. Okay, so symmetry. Do not forget that. Okay, look at the bounds. If you notice something sus about the bounds, negative pi over 2 to pi over 2, let's check if this is an odd function. And it is an odd function. So this equals to 0. Okay. All right. So what do we do here? This is an integral that you should have memorized, right? If an integration bee gives you this, right? Don't actually do it. Answer it with your memory, right? This is equal to a half of the derivative of secant x, which is secant x tangent x, plus the integral of secant x, which is ln of secant x, plus tangent x, plus c. Okay, all that times a half, so don't forget this half, all right? But if we were to integrate this, though, The way it looks like, so here's what it looks like, if you guys are curious. It is nasty. It is so nasty, right? The way it works is it's integration by parts. It's an integration by parts trig integral, right? So we split it up to secant x, secant square, and this becomes tangent x, and this becomes secant x, tangent x, and this is minus, right? So now we have this I integral, I, and we have secant x, tangent x, minus secant x, tangent square. Okay, now this tangent square becomes secant square of x minus 1 dx, and that's where the recursion comes from. So it's secant square, that's a bad c, secant square minus 1. So now this becomes integral of secant cube of x minus secant x dx. That's where all this comes from. So now this is all I equal secant x, tangent x. This is minus I plus, because this and this, they cancel out, so it's secant x dx. Okay, that's where this integral, that's where it comes from. So then 2I, that's where that half comes from. Secant x, tangent x, plus, and then the integral of secant x. Okay, this is where it all comes from. And then you divide by 2. So that's that whole process. Don't you dare do it. Don't you dare do it. We have bounds. We have bounds. We have bounds. This is equal to 0 because this is an odd function. How do I know this is an odd function? Well, this is sine cube. Sine's an odd function. And cubing it, it's still an odd function. So this is all 0. How dare you try to mimic the process with cosecant cube? I mean, if you do end up with an integral of cosecant cube, then I'm very sorry. Then I guess you might have to do a similar process. But if they have the bounds, symmetry. Do not forget symmetry. Do not forget symmetry. So this answer is 0. Okay. We are leaving it here. That's all the practice integrals for trigonometric integrals. Oh, there goes my phone. But yeah, that's it for this part. Part 5 we'll be working on trig substitution. So that's gonna be fun. So stay tuned for that. I hope this is very helpful, very useful for integration B. So yeah, thank you guys so much for watching. I'll see you guys in the next part.